Welcome to Sairam Triple A YouTube channel. Let us discuss Module 5 Power System Analysis and Stability. Right. So, in this, we are going to discuss introduction part of power system stability, ability to stable the system, and dynamics of a synchronous machine. Silent pole and non-silent pole machines will be there. Silent pole for less than 500 RPM speed. We are using in idle power plants because the speed will be less, and non-silent pole machines for the thermal power plant and the nuclear power plant because speed will be more than 500. More than 300 RPM, right? So simple systems, steady state stability, ability to stable the system and steady state, transient stability. So it's a, like a transient in a sense, less will be there. Ability to stable the system. So without affecting the overall system and equal area criteria factor affecting the transient stability. Let us see one by one in this module. Okay. Some of the definitions we'll discuss before entering into the topic. Stability, just one definition. When used to with the reference of the power system is that attribute of the system, part of the system which enable to develop restoration forces between the elements, therefore equal or greater than disturbing forces, so that restore state equilibrium between the element. This is the standard definitions of AIEE. So ability to stable the system, whatever it is happening in the power system components or power system. So again it come back to same position, stable position. So that's why it's called the stability. Next, steady state stability is the stability of the system under the consideration subject to gradual relative slow change in the load. So steady state in the sense slow change. Not sudden changes. So slow change in the load. Next, there is a transient state stability in the first module itself. Second module itself we discussed transient state and steady state, and then subtransient stability concepts. So again we are discussing here transient state stability. This refers to the stability of the system subject to the sudden large disturbances. The large disturbances may be brought about by sudden large changes in load, fault in the system, or loss of generation in the system. Next, dynamic stability. This is denoted the artificial stability given to the system by the action of automatic control devices like fast acting voltages, regulating and governors. Steady state stability limit. This refers to maximum flow of power possible through the particular point of the system without losses of the stability when the power increased gradually. Transit stability limit TSL. This refers to the maximum flow of power possible through a particular point without loss of stability when sudden disturbance occurs. So transient in the sense sudden variation, steady in the sense slow change, right? And power angle equations of a synchronous machine. Power angle equation basically it occur in the rotor of the synchronous generator, synchronous machine. Synchronous machine, either it may be a synchronous generator or a synchronous motor. Generator which converts mechanical to electrical, motor which converts electrical to mechanical. Particularly why they are taking this part, synchronous machine here. Power system analysis includes generation, transmission, distribution and utilization. So generation part, there we are using a synchronous generator, right? So synchronous machine is one of the most important elements of the power system. Synchronous generator converts mechanical into electrical form, fits into the power system network. On the other hand, synchronous motor draws electrical power from the network and convert into mechanical form. I told you, right? Synchronous generator and synchronous motor which converts electrical to mechanical, generator which converts mechanical to electrical. There are basically two types of synchronous machine, the round rotor, non-silent pole type, and then silent pole type rotor, right? And then power angle equations of non-silent pole synchronous machine. So I told you silent pole and non-silent pole are two different types of synchronous machines. Silent pole type of machine, there is a more comparison will be there in the silent to non-silent. Silent is a that diameter is large and the axle length is small, and air gap is non-uniform will be there, and it's for low speed applications like idle power plants. And non-silent pole, there is a unsilted portions we can call it as a poles, and poles are projected out from the surface in the silent pole synchronous generator. Here poles will be unsilted portion, we can call it as poles, right? And the air gap is uniform because uniform surface will be there. And also this non-silent pole generator we are using in thermal power plant, nuclear power plant, gas power plant, because the speed will be more, right? So in the case of non-cylinder synchronous machine, the rotor consisting of cylindrical structure having a number of slots, intervals, having outer periphery, cylinder for accommodating the field coils. So field coil is present, right? So in the synchronous generator, field coil is present in the rotor, and armature conductor placed in the stator. Because field is rotating, conductors are stationary, and conductor cuts the field. I mean rotating magnetic field. What happens? Induces EMF. Right, the air gap is uniform along the rotor periphery, and hence the flux linkages is also uniform. Therefore the machine offers the same reactance for the flow of armature current at all places. This reactance is called as a synchronous reactance of the machines. Right, next we have a steady state stability of two machine systems. Here two machines will be there, generator and motor. The one line diagram of two machine system interconnected to the transformer transmission lines, and shows figure 6.9. This one, we consider one of the machine as a synchronous generator, other one is a synchronous motor. See here, we considered here synchronous generator and synchronous motor. Generating part is synchronous generator, and output part, utilization part is synchronous motor. So this is a single line diagram of this uh, reactance diagram of this single line diagram of this figure. So just I'll draw and I'll tell you. So generator part is this one here, and this part is here, and this transmission line part is here, and XTV2 part is here, and motor part is here. This is a reactance diagram of this um, uh, two machine system, generator and motor. See, just generating station to the consumer side, motor side. Here it includes generation, transmission, distribution, and then utilization, right? So generation part is this one. This one is a transmission lines, and here distribution, and here there is a motor, right? So this is the overall figure for the reactance diagram for the this one, because all the generator reactance generators and transmission lines transformer represented in reactance values, right? Next we have dynamics of synchronous machine. Dynamics of synchronous machine in the sense, so half I omega square. Omega I is inertia, and omega is angular speed, right? Radian per second. So angular momentum. So kinetic energy of the rotor, right? So if suppose switch off the supply suddenly, what happens? So motor rotates particular time, right? So inertia will be there. That's what inertia will be rotor inertia will be less in the synchronous generator compared to DC generator. Keep it in our mind. So because the conductors weight of the rotor is less in the synchronous generator or synchronous machine. So that's the dynamics in the sense like moving in the synchronous machine, right? So